Have you ever had food poisoning that have ruined your entire day? Or a nasty stomach infections that made you so you would never eat outside again? Now, what if I told you the tiny culprit behind that misery is living inside you? Yes, it's called E. coli bacteria. Most of the strains of E. coli bacteria are harmless, even helpful. But some of them can turn dangerous, causing severe infections and even death. So here is a big question I want all of us to think about today. How do we kill those harmful bacteria without harming our body? And to answer this question, let me take you all inside this bacterial world just for a few minutes. Think of this bacterial cell as a small factory. It is protected by the outer wall, which is called cell membrane. And cell membrane has several tiny smart gates that controls what goes in and what goes out. And inside this factory, different kinds of proteins are constantly being produced. But here is the challenge. Some of those proteins do not do their job where they are made. They have to be transported across the membrane to do their function. And some of those transported proteins are toxins, which make us sick. And also some of those proteins are responsible for bacterial cell division and cell growth. So yes, just like any factory needs a shipping system, bacterial cell also need a transportation pathways to transport those protein packages across the membrane. And in E. coli bacteria, one of the transport pathways found is named as TAT system. You can think of this system as a specialized delivery gate. And this TAT gate is made up of several different kind of proteins, among which TAT-E is one. And I'm studying particularly this TAT-E protein. I'm studying the structure of this TAT-E protein, which is one of the components of this gate. Now, why this TAT gate matters today? Because of antibiotics. Our traditional weapon to fight against bacteria is losing its power because bacteria are being more antibiotic resistant and in fact already killing 1.3 million of people every year worldwide. Every time bacteria survives a drug, they come back even stronger. So instead of hitting them harder with more drugs, we need to outsmart them by targeting their weak spot. What is the weak spot? TAT gate, because of two crucial reasons. First, this TAT gate does not exist in human body. That means anything that targets this TAT gate only affects bacteria but leaves the human body unharmed. And second, studies have shown that bacteria struggles to survive if this gate doesn't work. But here is the surprising part. No current antibiotics has been designed to block this. So it is an untapped opportunity. Now imagine designing a drug molecule that can block this TAT gate like a key. Gate will be blocked and bacteria will not be able to transport protein materials. That means no toxins, no cell growth, no survival. Bacteria will start to suffocate from inside and eventually they will die. But to design such drug molecule, first we need to know how that TAT door looks like, its shape, its function, structure. Yes, that's where my research comes in. I'm studying the structure, dynamics, and topology of this particular TAT-E protein in the lipid membrane. In simple terms, I can say that I'm studying about the architecture of this TAT door. Now, what I'm doing actually in my lab. So in Dr. Lorigan's lab, I recreate what happens in nature. I synthesize TAT-E protein. I build membrane environment just like it exists in bacterial cell membrane. Then I carefully insert this TAT-E protein into the membrane. Now once this is placed perfectly, my sample is ready, which mimics the real environment. After that, I study it using advanced spectroscopic techniques. You have probably heard about MRI scans. This technique allows doctors to see inside human body without surgery. What I do in my lab is conceptually similar but at much, much smaller scale. Instead of scanning a human body, I scan a single protein using different techniques like CD spectroscopy, EPR spectroscopy, and NMR spectroscopy. Each technique reveals the different pieces of the puzzle. But altogether, these techniques reveal how that E protein is structured and how they behave in lipid membrane. Yes, that's how my study brings all of us one step ahead towards understanding the architecture of this STAT gate. And once we understand this STAT gate fully, with that information, drug designers can start designing molecules that can disrupt this STAT gate. Because we cannot target anything that we don't understand. Understanding is the main first step towards the safer and smarter antibiotics, saving millions of lives. So that's how my research lays the foundation for next generation of safer and smarter antibiotics, leaving our body unharmed. Now remember, we started with the question, how do we kill harmful bacteria without harming our body? And the answer is very simple. Don't destroy the whole factory. Just seal its gate. Yes, that's how we can win the war against infection smartly and precisely. Thank you.